Top dogs, and welcome to my YouTube channel. So if you haven't subscribed, please hit the subscribe button to help me improve my channel. Okay, so in this series I'm going to show you how to solve all of ordinary differential equations from first order, second order to nth order. So this is going to be a series of solving the differential equations. Okay, so first let's do introduction of ODEs. We're going to start with the notation and definition. So our definition, let's start with the function f. So assume that the function f is continuous in the interval AB, closed interval AB is continuous in the interval A, B, and differentiable in the open interval AB. So we are going to assume that we have a function f which is differentiable and continuous in the interval AB. Okay, so what's the derivative of that function? If that function is a function of x, if our function is a function of x, meaning that x is an independent variable and f is a dependent variable, then we can, what's the notation for the first derivative? So the notation for the first derivative of that function is going to be given by this, which is the same as df divided by dx, since x is a independent variable. And the second derivative of that can be given by of x can be given by d squared of f divided by dx squared. And the third derivative can be given by d cube of f over dx cube. And since here we're going to solve the equations up to the nth order, so if we solve the equations up to the nth order, therefore we must also give the notation for the nth derivative. So the notation for the nth derivative is going to be, the notation for the nth order is going to be f of n x being d of n f divided by d of x n. Okay, so this is going to be the derivative to the nth order. So now let's go to the definition of what's an ODE. So an ODE is going to be the function that consists of its and independent variables, independent and dependent variable. So it's an equation that consists of a derivative of a function, derivative of dependent variable and independent variable and dependent variable. So independent variable here, now let's deal with y. Let's change x and deal with y. So if we are solving the y of x, so y is going to be dependent variable, this y here is going to be dependent variable, and this x here is going to be independent. So the derivative, the function that consists of this and its derivative, we are calling that an ordinary differential equation. Okay, so to write example of ordinary differential equation, I'm just going to do this. So this, remember that is going to be the first derivative according to our notation. It's going to be the first derivative according to our notation, and it's given by x squared. So since x squared is an independent variable, I can add this by y. So y is a function of dependent variable. Okay, so this is an example of ordinary differential equation. So an ordinary differential equation is an equation that consists of a derivative of the dependent variable, independent variable, and dependent variable. Consists of all those things. So that's going to be an ordinary differential equations, ODE. So let's go to a scalar partial differential equation, or PDF. So PDF is going to be the same as this one, but here we are going to have a function. Consider function u that it's given by the function of x and y. So actually u is going to be dependent variable. Sorry, u is going to be dependent variable, and x and y are going to be, these x and y, they are going to be independent variables. They are going to be independent variables. So from calculus, we know that if you want to find the du is going to be given by, we are going to take the partial derivative of u with respect to x, which is a partial of u with respect to x, and we add by the partial of u with respect to y. So we are also going to deal with such equations here. So those who are going to call them a scalar partial differential equations. You can see where this term is coming from. The partial differential, here you have a partial derivatives. So those partial derivatives are the one that gives you the partial differential equation, or PDE. Okay, so now let's move on to classifications. So we are going to classify the ordinary differential equations. So to classify an ordinary differential equation, you're going to classify it according to order, linearity, homogeneity, and finally degree. So we're going to start with order. So let me just write a simple ordinary differential equation. Okay, so let's have this ordinary differential equation here, which is a d squared of y divided by d plus x squared dy over dx cube plus y to the power 4 is equal to 0. So here let's give the order of this and decide whether this is a linear or is a homogeneous. All right, so first, the order of differential equation is going to be the highest derivative in our equations. So here we know that y is going to be the dependent variable and x is going to be independent variable, and order of these, we're taking the highest derivative of the function. So the highest derivative here is a second derivative. This is the highest derivative, and take note, don't be confused by this thing. Let me show you this thing here. You see this, don't let this confuse you. It's like some people they tend to say this. Let me show you what they're saying. It's like if you have a dy over dx all cube. Some people tend to say this is the same as dy over dx cube, and then they say this is the third derivative of the equation, and which, if this is true, this is the third derivative, but this is not equal to that, so therefore this is wrong, because these two things are not equal. So don't and ever say that or write something like that. No, you have to know that these two things are not the same. Okay. So now let's classify this one here according to order. So order is going to be the highest derivative. So what's order? Order was saying is the highest derivative. Okay, so the highest derivative here is 2, is this second. So since that's highest derivative, we are going to say this is a second order differential equation. So this is going to be a second order differential equation. And then we go to linearity. So linearity, we're going to check the power. Here for the linearity, we're checking the power of dependent variable. We're checking the power of dependent variable. So power of dependent variable, you know that from polynomials, if you have a polynomial is equal to x, this is, but if f of x is x squared. We are decreasing by 1. This is non-linear. If f of x is given by x cube, this is also non-linear. So an equation is linear only if the power of dependent variable is 1. So if the power of dependent variable is not 1, therefore it's non-linear. So let's check this one here. What's the dependent variable here? Dependent variable is y. So if you can check here, our y in this case here has a power of 1. Our y here is going to have a power of 3 because of this, and our y here has a power of 4. So we conclude by saying this is non-linear. This is going to be a non-linear. And there's another thing that sometimes confuses people. Let's say you have another equation that's given by dy over dx is equal to x plus sine of y. Is this linear or non-linear? Tell me. Okay, so I'm going to give you an answer. So since here this is a sine, and we check the power first. The power here tell us that this is it's a linear because it has a power of 1. But we come here we have a sine of theta. So if you have a sine of theta, what are you going to say about that one? We have a sine of theta. So if you have a sine of theta, that means sine of theta of y, not sine of theta. Sine of y is a non-linear, right? So because sine of y, let's draw that. If we can draw a function of sine of y function is going to be something like this. So since it's going to be, we know that the sine function starts here and goes there and ends here. So this is a sine function. This is a sine function where this is a theta, or we can say this is y, and then this is a sine of y. So this is a sine function. So you see that's non-linear. So since the sine function is non-linear and the sine function is a function of dependent variable, so therefore this makes this expression to be a non-linear. Another example that still confuse people is this one here. Let's do the last one. That's is a confusion. What if you have something like this? What if you have something like this? You have something like this. You have dy over dx is equal to x plus sine of x. Okay, so now we check the power of dependent variable. So the power of dependent variable here is still 1, telling us that this is a linear. And we go here, we don't have, but we have this sine theta. So people tend to say, okay, no, I have sine theta here, and sine theta is a non-linear, therefore this expression is going to be non-linear. Nope, that's wrong. The only thing that can make this to be non-linear is if you have a function of dependent variable here, and that's non-linear. So therefore it's going to make this expression to be non-linear. But if you have a sine of x, which is sine of x is still non-linear, but that's not the independent variable. X is not a dependent variable, so it's independent variable. Therefore this expression still it's a linear. All right, so don't confuse this with that other one. Okay, so lastly we're going to check the homogeneity. So the homogeneity actually here is like if we can substitute the independent variable, and that is not going to change the equation, our equation. So let's say I'm just going to give you an example of this one. Let's say we have a d squared of y divided by dx squared plus y plus d of y over d of x is equal to times x here is equal to 0. So what we're doing, we multiply the independent variable, or actually we should the independent variable by k, and see whether that's going to change our equation, right? So here let's come to this one first. So for this one it's going to be d squared, and where we had y we can put k, we can say this is ky, and then we divide by dx squared, plus here we have y, and then now we're going to put ky plus x d, here we had y, and then we say this is ky, all right, and then we divide by dx is equal to 0, and we solve this equation again. So here this is not going to change anything, because when you solve this nothing is going to change. So when you're trying to solve this equation, what you're going to get is just we're going to take k out here. So if we take k out, this is going to be d squared of y divided by dx squared plus y plus x d dy over dx, which is going to be equal to 0. So here can you see that k is equal to 0, going to be equal to 0, the whole of this. So you get your original equation again. So therefore we say this kind of equation where you can multiply the dependent variable, or you substitute where was the dependent variable by k and the first the first degree of dependent variable. So if it doesn't change, therefore you say it's a nonlinear. Okay, it's a homogeneous. Sorry, if it doesn't change, you say it's a homogeneous, not nonlinear. So homogeneous, actually, for this homogeneous thing, for homogeneity, you multiply. What you are doing here, you multiply or you substitute. Let's use the word substitute. Multiplication is not good. You substitute dependent variable by k and first degree of that dependent variable. So the first degree means that what you are substituting by the constant k and y, which is a first prime. So that's why I was saying that's a first degree. Okay, so let's move on to another one. Let's move on to degree. Okay, so I'm just going to show you how to find a degree. So degree, here you are checking the power of dependent variable in the highest derivative. The power of dependent variable in the highest derivative. So actually you are just going to check the power of dependent variable in the highest derivative. Power of dependent variable in the highest derivative. So let's do that. Let's check the power of the dependent variable in the highest derivative. Okay, so what we're going to have, let's say we have this one here. We have this, which is the d, so d squared of y squared over d of y squared is equal to the d y over dx plus 3x plus sine of x plus d cube of y over dx. So what's the degree of this one? What's the degree of this? So we're checking the power of dependent variable in the highest derivative. So first let's decide what's the highest derivative. So the highest derivative is this one here. Can you see? This is going to be the highest derivative. This one here. This is our highest derivative. So since this is our highest derivative, what can we say? What can we conclude? conclude by saying that if this is our highest derivative, therefore the degree of this function is going to be 1, first degree. This is going to be first degree. This is a first degree. You check the power of dependent variable in the highest derivative. So you found that the power of dependent variable in the highest derivative is 1. Therefore, you are going to say this is a first degree ordinary differential equation. Okay, so stay tuned, and in our next videos we're going to do the type of, before we can move on, let's do the type of coefficients. We're not done. After the degree, you have to classify an ordinary differential equation as a type of coefficient. What kind of coefficients do you have? Okay, so I'm just going to take one of these, which is let's take which one can we take? Okay, let's take this one here and see. So why it as a kind of the kind of coefficients that we have. So here, the kind of coefficients that we have in this one, we have this is going to be the variable coefficients. So the kind of coefficients that it's easy. Actually, the coefficient, to classify it according to the coefficients, it's the easiest step, because here if you have a dy divided by dx plus x squared plus y dy over dx is equal to 0. This, we say this is a variable coefficient. You see that this derivative is multiplied by y, so therefore we are saying it's a variable coefficient. Even if it's multiplied by x, you are saying it's a variable coefficient. Even if you had x here, here like was x, so if it was x here, you could say this is still the variable coefficient. But if you had something like dy dx plus x squared plus dy divided by dx squared is equal to 0, you are saying this is a constant coefficient, because here you have 1 and here you have 1. Actually, so you are checking the coefficients of those derivatives. So if you find that the coefficients of those derivatives is a constant, you are saying it's a constant coefficient. If it's a variable, then you're saying it's a variable coefficient. Okay, so in our next video we're going to do the integration of ODEs, and after that we're going to go to a classification of the first order ODEs and keep on solving the reducible equations, and we're going to solve also the exact equations, and we're going to keep going. Thanks for watching my video, and if you didn't subscribe, hit the subscribe button.